The hot strip mill covers a vast area of 15,000 square meters, roughly the size of 2 football fields. It has the capacity to store up to 2,500 slabs, each slab being a large piece of steel ready for processing. The hot strip mill operates at an intense heating temperature of 1,250 degrees Celsius, which is crucial for transforming steel slabs into thin, malleable strips. This extreme heat allows the steel to become pliable enough for rolling into various thicknesses and widths. To maintain this high temperature consistently, the mill consumes an enormous amount of energy annually, equivalent to the electricity usage of around 200,000 households. The press in the hot strip mill exerts a massive force of up to 2,200 tons, compressing the steel slabs with immense power. This process reduces the width of the slabs by 300 millimeters, shaping them for further processing. The roughing mill is a critical stage in the steel production process, where large slabs are reduced to more manageable sizes. Powered by 2 drive motors, each with an impressive 20 megawatts capacity, the mill can generate the substantial rolling force required to shape the steel. With a rolling force rated at 5,500 tons, the roughing mill is capable of exerting intense pressure on the heated slabs. Initially, the steel slabs enter the roughing mill with a thickness of approximately 250 millimeters. As the slabs pass through the mill's powerful rolls, they undergo significant deformation, with their thickness being reduced to just 45 millimeters. This reduction is crucial as it prepares the slabs for the subsequent stages of rolling, ensuring they are thin enough to be processed further into coils. The roughing mill's high drive power and rolling force enable it to work on steel slabs that are still at high temperatures, maintaining their malleability while ensuring the structural integrity of the metal. The finishing mill uses powerful 3x3 megawatts, 440,000 HP, drive motors to reduce strip thickness to 25 millimeters to 1.6 millimeters and widths up to 2,020 millimeters. The cooling section rapidly cools steel strips, handling up to 100 million cubic meters of water annually, equivalent to the needs of 80,000 households. It lowers the steel's temperature from 750 degrees Celsius to 50 degrees Celsius. The coiler winds steel strips into coils with a diameter of 2,100 millimeters, weighing up to 35 tons. Each coil can contain a strip up to 1.5 kilometers in length. The steelmaking process begins with melting scrap iron, the primary raw material, in an electric furnace. This process is critical for producing semi-finished products called slabs, which are essentially large steel blocks used in various manufacturing applications. Initially, scrap iron undergoes thorough inspection to remove any non-ferrous metals, such as copper and tin. This step ensures that the raw material is free from contaminants that could affect the quality of the final product. The blended scrap iron is then placed in large baskets and transported to a massive electric furnace with a capacity of 200 tons. The furnace is one of the largest of its kind and is operated from a central control room. Inside the furnace, the scrap iron is melted using high-energy electric arcs and oxygen. The electrodes that generate these arcs are held by arms made from aluminum alloy, chosen for its excellent conductivity and strength. The molten steel is refined at temperatures around 1,600 degrees Celsius. During this phase, known as slip casting, slag is easily separated from the molten steel, reducing impurities and ensuring a cleaner final product. Following this, the molten steel is transferred to a refining furnace where impurities are further removed through reduction, and the chemical composition is adjusted by adding necessary elements. Optical emission spectrometers continuously monitor the composition of the molten steel to ensure it meets required specifications. In the refining furnace, a turret system facilitates uninterrupted continuous casting. The molten steel is then poured into molds through a tundish. As it cools, the steel is drawn out of the molds at a consistent speed while the molds oscillate up and down, forming the slabs. The continuous casting facility is equipped with advanced technologies, including electromagnetic stirring devices and cooling systems, to maintain uniform internal quality and produce high-quality slabs consistently. Casting a marine diesel engine block at MAN Diesel and Turbo, Augsburg. The process of casting a marine diesel engine block at MAN Diesel and Turbo in Augsburg is a monumental task that blends advanced engineering with sheer physical prowess. As one of the largest foundries in Germany, this facility is responsible for producing engine blocks that power some of the most massive ocean-going vessels in the world. When one steps into the foundry at MAN Diesel and Turbo, the first thing that strikes is the scale. Everything is oversized, from the molds and cores to the furnaces and cranes. This isn't a typical factory setting. It's a place where metal meets fire on a grand scale. Workers clad in specialized suits and helmets navigate through the foundry, their gear a necessity to withstand the extreme conditions they face. The environment is reminiscent of a scene from a dystopian novel, where men and machines collaborate in a dance of fire and steel. The journey to create a marine diesel engine block begins with the preparation of the mold. This mold is no ordinary structure. It is a massive assembly made from a mixture of sand and resin, which forms a hard, heat-resistant shell capable of withstanding the molten iron that will soon be poured into it. The mold is created with exacting precision, down to the millimeter, as any deviation could compromise the integrity of the final engine block. Creating the mold involves assembling several parts, including cores, that will shape the internal passages of the engine block. These cores are made from the same sand-resin mixture and must be handled with extreme care. Once positioned within the mold, they are coated with a ceramic fireproof paint known as slip, which prevents them from melting or deforming when the molten iron is poured. The entire assembly process is a delicate balance of strength and precision, as the cores must be placed with millimeter accuracy to ensure the walls of the engine block are of the correct thickness. While the mold is being prepared, another crucial process is taking place: melting the iron. The foundry uses scrap metal, primarily old iron and steel, which is melted down in furnaces that are large enough to handle up to 120 tons of metal at a time. This scrap metal, which can include old ship engines and other large metal objects, is first gathered and then fed into the furnace by a massive magnet. The furnace is heated to temperatures exceeding 1,500 degrees Celsius, where the scrap metal liquefies and becomes the molten iron that will form the engine block. This stage of the process is both time-consuming and intense. It takes about 8 hours to melt enough iron to fill the mold, and the process continues well into the night, often until 3 a.m. The molten iron is then transferred into ladles, large containers that can hold several tons of the molten metal, ready to be poured into the mold. The actual pouring of the molten iron into the mold is a spectacle of precision and coordination. 4 ladles, each filled to the brim with molten iron at around 1,482 degrees Celsius, are brought to the mold by overhead cranes. The mold, buried under 900 tons of weight to prevent it from shifting or cracking under the immense pressure of the molten iron, is ready to receive the iron. As the ladles are positioned above the mold, the iron begins to flow, filling the intricate cavities and channels formed by the cores. The cooling process is one of the most critical stages, as any rapid cooling could result in defects. The slow, controlled cooling ensures that the engine block maintains its structural integrity and that the metal crystallizes in a way that maximizes strength and durability. With the casting process complete, the engine block undergoes several finishing processes. The block is cleaned, and any excess material is removed. It is then machined to precise specifications, with holes drilled for cylinders, crankshafts, and other components. The crankshaft, one of the largest single parts of the engine, is installed next. This component, weighing 25 tons, is responsible for converting the linear motion of the pistons into the rotational motion that drives the ship's propeller. The installation of the crankshaft is a meticulous process, requiring precise alignment and careful handling to avoid damaging this critical part. Once the block is fully assembled, it is subjected to rigorous testing to ensure that it meets all specifications and standards. Only after passing these tests is the engine block ready to be shipped and installed in a ship, where it will serve as the heart of a vessel for decades to come. Steel production in an electric arc furnace. Steel is a fundamental material that underpins modern civilization, found in everything from skyscrapers to automobiles. It's indispensable, with countless industries relying on its strength, durability, and versatility. Germany is a leading producer of steel, generating approximately 44 million tons annually. A significant portion of this steel is produced using scrap metal, a vital raw material that underscores the sustainable aspects of the industry. At the forefront of this production are the German stainless steel works in Witten, recognized globally for their expertise in high-alloy specialty steels. These steels are engineered for demanding applications where strength, corrosion resistance, and other specific properties are crucial. The heart of their production process is the electric arc furnace, a massive and powerful machine that plays a critical role in transforming scrap metal into high-quality steel. The process begins with scrap steel being loaded into the electric arc furnace. Every 90 minutes, the Witten steelmakers energize the furnace, initiating a controlled inferno that melts the scrap metal. This process is intense, with the furnace reaching temperatures exceeding 1,700 degrees Celsius. These extreme conditions are necessary to break down the scrap into molten steel, which can then be refined and alloyed to meet precise specifications. Working in close proximity to the furnace is a physically demanding job. The conditions are harsh, with intense heat and the need for constant vigilance. The furnace, often referred to as a hell furnace, processes approximately 75 tons of steel per hour, making it a highly efficient but challenging environment. After each batch of steel is tapped from the furnace, the door must be cleaned of the remaining slag, a byproduct of the melting process. Given the extreme temperatures, this task is too dangerous for human workers and is instead performed by specialized machines designed to handle the intense heat. Once the steel is removed from the furnace, its journey is far from over. The still glowing steel blocks are transported to a rolling mill where they undergo further processing. Here, the steel is hardened and shaped into its final form. Operators like Stefan Seeweg use joysticks to control the heavy machinery that manipulates these massive blocks, moving them between counter-rotating rollers that flatten and stretch the steel, preparing it for its eventual use in various industries. Each year, the Witten facility processes around 500,000 tons of scrap steel, converting it into high-alloy specialty steels. These products are essential for a wide range of applications, from automotive manufacturing to aerospace, medical technology, and even the offshore wind industry. The ability to recycle and repurpose steel highlights the material's sustainability, as it can be melted down and reused repeatedly without losing its essential properties.
In the first step, a micrometer is employed to meticulously measure the height of the bearing's outer ring. This precise measurement establishes a baseline for further analysis and ensures dimensional accuracy of the component. In the second step, a specialized instrument is utilized to gauge the height error of the bearing's outer ring. A standard block is incorporated into this process to minimize inaccuracies. To enhance precision, measurements are conducted multiple times from various locations across the bearing. Additionally, strategic marks are made on the bearing surface to prevent installation errors, ensuring proper alignment and function within the rolling mill machine. This meticulous approach guarantees that the bearing meets stringent quality standards and performs optimally in demanding industrial environments. In the final step, precise measurements of the bearing's outer and inner rings lengths are taken. Utilizing calibrated instruments, technicians carefully assess the dimensions of both components to ensure they meet exact specifications. This meticulous evaluation guarantees proper fit and functionality within the rolling mill machine. Accurate measurements of the outer and inner ring lengths are essential for maintaining the structural integrity and operational efficiency of the tapered roller bearing. Feeding of the rings. The process begins with the automated feeding of the rings, carefully sorted and positioned for further assembly. Measuring of the outer ring. Each outer ring undergoes meticulous measurement to verify its dimensions, ensuring consistency and accuracy in the final product. Measuring of the inner ring. Similarly, the inner ring is measured to exacting standards, guaranteeing a perfect fit and smooth operation. Selection of balls. Next, the optimal balls are selected based on size and quality, crucial for the bearing's performance and durability. Joining the rings. The outer and inner rings are precisely joined, forming the foundational structure of the bearing. Fitting of the balls. Each ball is carefully fitted into its designated position within the assembled rings, utilizing automated machinery for precision. Spacing of the balls. The spacing between the balls is meticulously controlled, ensuring uniform distribution and optimal load distribution. Fitting of the cage. The cage, which holds the balls in place, is fitted snugly into the assembly, providing stability and reducing friction. Cage riveting. Finally, the cage is securely riveted into place. Forging initiates by heating high-quality steel to its optimal temperature, ensuring malleability. Through controlled hammering or pressing, the heated steel is shaped into rough rings. This crucial step sets the foundation for subsequent machining processes, ensuring the integrity and strength of the roller bearing components. Turning. Next, the rough rings undergo turning, where they are machined to achieve specific dimensions and smooth surfaces, ensuring uniformity and precision. Cage drilling. Roller cutting. Raw materials are shaped into individual rollers through cutting processes. Heat treatment rollers. The rollers undergo a specialized heat treatment process to enhance their strength, hardness, and resistance to wear. Grinding. Both the rollers and rings undergo precision grinding to achieve tight tolerances and smooth surfaces. Quality control throughout the manufacturing process. Assembly. Once all components pass quality inspection, they are carefully assembled, ensuring proper alignment and fitment to achieve optimal performance. Packing. After assembly, the bearings are packed securely to protect them from damage during transportation and storage. Mounting is the culmination of the bearing manufacturing process. Technicians carefully install the bearings into their designated machinery or equipment, ensuring precise alignment and proper fitment. Securely mounted bearings facilitate smooth rotation within the machinery, transmitting loads and minimizing friction between moving parts. Their correct installation is vital for the efficient operation of the equipment, ensuring longevity and reliability in various industrial applications, from heavy machinery to precision instruments. ARB Bearings boasts a comprehensive product range, encompassing an impressive array of 1,400 different sizes of bearings, catering to diverse industrial applications and requirements. The range includes a multitude of bearing types, such as deep groove ball bearings, cylindrical roller bearings, spherical roller bearings, angular contact ball bearings, thrust bearings, and more. Each type is available in a wide range of sizes, configurations, and specifications to suit different machinery and operating conditions. With a state-of-the-art manufacturing infrastructure and advanced production techniques, ARB Bearings has the capability to produce a staggering 12 million bearings per annum. This high production capacity is a testament to the company's efficiency, technological prowess, and commitment to meeting market demand. The manufacturing process at ARB Bearings is characterized by precision, consistency, and quality control at every stage. From raw material sourcing to final product inspection, stringent quality assurance measures are implemented to ensure that each bearing meets the highest standards of performance and reliability. Advanced machinery, including fully automatic CNC grinding and super finishing lines, is employed to achieve exceptional levels of precision and surface finish. Computerized and atmosphere-controlled heat treatment systems ensure the durability and integrity of the bearings, enhancing their resistance to wear, fatigue, and corrosion. Furthermore, ARB Bearings adheres to strict quality control norms and certifications, including ISO TS 16949-2009 and OSIS 18001, ensuring compliance with international standards and regulations. The company's commitment to quality is further reinforced by comprehensive testing facilities, including vibration, noise, endurance, and life testing, which guarantee the reliability and longevity of its products. The installation commenced with the preparation of Tub 1 and Tub 2, critical components of the cranes. These massive tubs serve as the base for the crane's operation, providing stability and support. Following the tub installation, Crane House 1 was positioned atop Tub 1. This structure houses vital components of the crane's machinery and control systems. Slew bolt tensioning, a crucial step in ensuring the stability and functionality of the crane, was carried out. Proper tensioning of the slew bolts secures the crane house to the tub, preventing any unwanted movement during operation. With Crane House 1 in place, attention shifted to the installation of Winch Room 1. This compartment houses the winches responsible for lifting and lowering heavy loads. Meanwhile, at Husman, China, Boom 1 underwent load-out procedures. This framework plays a vital role in controlling the angle and position of the crane's boom during operation, requiring precise rigging to ensure optimal functionality. Once rigged, luffing frame 1 was loaded out from Husman, China, ready to be transported to the installation site. The boom and luffing frame arrived in Singapore, marking a significant milestone in the installation process. Upon arrival at the installation site, luffing frame 1 was carefully installed, completing a crucial stage in the crane assembly process. Precision and attention to detail were paramount to ensure the frame's proper alignment and functionality. With luffing frame 1 in place, attention turned to the installation of Boom 1. This involved careful positioning and attachment to the luffing frame, ensuring seamless integration and alignment for optimal crane performance. Crane 1 installed, Crane House 2 installation. With Boom 1 successfully installed, Crane 1 was now fully assembled and operational. Meanwhile, Crane House 2 was installed atop Tub 2, mirroring the process carried out for Crane House 1. Winch Room 2 installation. Winch Room 2, the counterpart to Winch Room 1, was installed with precision, completing the installation of the crane's lifting mechanisms. Winch Room Lower Shaft installation. Boom 2 installation. The final steps of the installation process involved the installation of Winch Room Lower Shaft and Boom 2. These components were carefully integrated into the crane assembly, ensuring the completion of both crane units. With meticulous planning, coordination, and execution, the installation of 2x10,000 mount Hussmann tub-mounted cranes for Hieronymus Sleipnir was successfully completed, ready to undertake heavy lifting operations with precision and reliability.